We will now answer the 4 loopy questions for the algorithm given in the previous video, which is displayed in the code and flowchart here. The first loopy question is, does it start right? We want to show that the initialization makes the invariant p true. In other words, does the execution of z becomes 0, k becomes m, with q true, terminate with p true? To show this, we first write the invariant p. Since the initialization sets z to 0 and k to m, we replace z and k with these values in p, as shown in bold here. We can see that the first part of the invariant is true based on the precondition, q. We can see that the second part is true because m.m-1 is an empty range, and the sum of the elements in an empty range is 0. Therefore, the answer to the first loopy question is yes. The second loopy question is, does it stop right? We want to show that when the loop terminates, the post condition R is true. We do this by showing that when the loop guard is false and the invariant is true, R must be true. For this loop, we ask the following. Does k greater than n and p imply R? First, we observe that if k is greater than n and p is true, k must equal n plus 1. Next, we substitute k with n plus 1 in p. Simplifying the second part of the expression, as shown here, gives us the postcondition, R. The answer to the second loopy question is yes. The third loopy question is, does each iteration make progress toward termination? We have bolded the relevant code in the flowchart. As you can see, on each iteration of the loop, k is incremented by 1. At some point, k will reach n plus 1, and the loop will terminate. The answer to the third loopy question is yes. The fourth loopy question is, does the loop body keep invariant p true? In other words, does the execution of z becomes z plus k becomes k plus 1, given p, combined with k at most n, terminate with p true? For the first half of p, we can easily see that if k is at most n, and we increment k by 1, then k is now at most n plus 1. For the second half, we want to show that z remains the sum of m dot dot k minus 1. When execution of the loop body begins, this is true. After executing the first line, bolded here, z equals the sum of m dot dot k. This can be rewritten as z equals the sum of m dot dot k plus 1 minus 1. The next line of code increments k by 1. K is now equal to k plus 1. This means that we should replace k plus 1 in the expression with k. Z remains the sum of m dot dot k minus 1. We have now shown that the loop body keeps the invariant p true. The answer to the fourth loopy question is yes. The answer to each of the loopy questions is yes. This means that the loop has been proven correct. You might notice that it took a lot of words to prove that the loop was correct. If you want to explain the correctness in detail to someone, you must do this. But as you become more experienced, you will check the loopy questions in your mind with ease. You will find that this is far less work and less error-prone than working without the invariant and trying to understand the algorithm.